Good day, students. This lesson is on plate tectonics. This lesson follows our discussion on continental drift and seafloor spreading. Just a reminder, continental drift was the idea proposed by Alfred Wegener, and his thoughts were that the continents were drifting, they were moving, that they had started off as one large continent known as Pangaea and had drifted apart. Later on, in about the 1940s, they developed on his ideas and started to come up with the idea of seafloor spreading, where they actually looked at the new ocean seafloor being developed at areas known as the mid-ocean ridge from magma coming up through the surface. This then continued on into the 1960s and really started to look at our crust and looking at the continents themselves and looking at how things moved and come up with this idea of plate tectonics. So what scientists found is that in the 1960s, the Earth's crust is broken into pieces known as plates. So they really kind of decide that, you know what, it's not one solid piece. There's individual components, and they're moving in different directions depending on what they are. So if we look down here on this map, we can actually see the different plate boundaries as represented just by a line. And the arrows represent if it's a divergent or convergent boundary, and we'll talk a little bit about that more. Divergent means it's going away from each other. Convergent means it's coming together. So if we look at the Eurasian plate and the African plate, we can see that that's a convergent boundary. They're coming towards each other. Whereas if we look at the Pacific plate and the Antarctic plate, they are going away from each other. So we'll talk more about those different plate boundaries, but this is something that you should be familiar on how to read this kind of map and so on. So looking at the different plates, they get broken down into these sections, but why do they move? And so we have to look a little bit about the structure that we see in our Earth components. So up here we see that we have continental crust. We can see that we have oceanic crust, so there's two different types of crust. We then have this layer known as the lithosphere, and what the lithosphere is it's a cold, rigid outermost rock layer made from the crust and upper mantle. And what we can see from that is it's just a real rigid part, and a lot of times it goes, when we talk about the lithosphere, it's the crust section and then the very uppermost part of that mantle, and the reason that upper mantle goes along with the crust is it's very hard and rigid, very similar to the actual crust. And what that does is we see that's what forms the plates. That's what the plates are actually made from. Now the layer underneath, known as the asthenosphere, and a lot of times you hear this kind of plastic term that goes along with it because when it's heated up, it has the ability to be molded. It can be moved. It's almost like Play-Doh. And so that allows for the actual movement of the plates. So without that layer, we would not have plate tectonics. And we'll talk more further on kind of that's the driving force of plate tectonics, but it's really important that asthenosphere allows for the motion. It kind of causes a conveyor belt kind of concept with it. The first plate boundary that we're going to look at is a divergent plate boundary, and divergent means to separate. So really what we're going to look here is that we're going to see two plates are going to separate. And what we'll see is that this is going to occur at the mid-ocean ridge. And we've talked about that. It should be familiar to you from seafloor spreading. The MOR, again, just to remind you, is the mid-ocean ridge. And that's where we're going to see new oceanic crust being formed. So what happens is as those two plates start to separate, and we can see down here in the image that as they separate, it allows for the less dense magma that is rising to come out. And as it cools, it starts to become more dense and settles. And then as new stuff comes up, it causes it to push out and push out. And so we form a new floor based on that. We also can see that they will form a rift valley when it occurs in the middle of continents. So we can not only see this in the ocean, but also on land. And when those plates are starting to pull apart, we call that a rift. And an example of that would be the Eastern African rift. And a lot of times they're valleys, and it looks like the ground is just pulling apart. The second type of boundary we're going to talk about is the transform boundary. And the key idea with this is that the two plates are going to slide against each other. And what happens is as these plates slide, you get friction, which is a force we've talked about in the past. And it's not just a nice even flow. But what we'll see is they get stuck to each other. And they'll stay stuck for a while. And then when there's enough force pushing against them, they will release. And they tend to release with great force. And that's really what creates the earthquakes. So we usually think of a transform boundary, the main kind of feature that will form. Sometimes we talk about faults and earthquakes. Probably our most famous example of a transform boundary is San Andreas Fault. The third type of boundary that I want to talk about is a convergent boundary. And what that is when two plates come together. And we can look at a couple different types. We can look at an oceanic to a continental plate coming together. We can talk about a continental plate coming together, and an oceanic plate coming together. So there's three main types we look at that. Key thing to look at that is the fact that you have two plates collide. The denser plate sinks below the other plate through a process known as subduction. And what subduction is it's this idea, let me just get this erased for you so you can copy down. The subduction is when one plate is denser than the other plate. And so as the denser plate sinks underneath the other plate, that's known as subduction. So this area where the one plate sinks under the other, and we can see that going on right up in here, that is known as the subduction zone. If we talk about an oceanic and a continental plate, now oceanic plates are going to be denser because they're very rich in iron and magnesium. They have basalt, they're igneous rock, they're very dense. And so they're going to have more density to them. They're going to sink under a continental crust. The continental crust has got lighter minerals and rocks, and so it will tend to float. So as it sinks underneath, it can form a deep ocean trench. So right in here you can see kind of the crease here, that's known as the deep ocean trench. And then also on top here on the continental crust, we can see volcanoes form, because as this kind of plate sinks underneath, it will melt over time. It helps to produce magma and that kind of stuff that can be part of this volcanic chain. We can also look at an oceanic, and it's going to be the same idea, except whatever plate is more dense, that is the one that's going to sink underneath. So again, it looked very similar to this diagram up here. It's just you'd have two oceanic plates come together, and whatever one is more dense is going to be the one to sink. The third type of convergent plate boundaries would be looking at a continental to continental. And in this case, they're going to be about the same density. So you're not going to have one that's going to sink under the other. So as they come together, it's almost like they buckle. They push against each other, and there's nowhere to go other than up. And we get this process that we talked about, like with the rock cycle and that, looking at this term of uplift, where it's the movement of rock material in an upward direction. Well, that's what really occurs here. And what we're going to see form is we're going to see mountains form, because that uplift is going to cause a large amount of material to move upward. So really the kind of action that we see here is uplift, and an example would be the Himalayas, which is shown here in the diagram. So some of these mountain ranges, when we see them on a continent where you're looking at two continental plates coming together, that is formed from the mountains. Those mountains are formed because of that uplifted material, because neither plate is going to sink. To summarize up our discussion on plate tectonics, just a reminder with you going over this, that plate tectonics, what that means is that the crust is broken into sections known as plates. These plates can be found to form three different types of boundaries. We can see divergent, convergent, transform. And the key thing to realize with these different boundaries is that they show a great relationship of where most volcanoes and earthquakes occur. So for example, on a divergent plate boundary, which is where we're going to see the plates are starting to move apart, we can see volcanoes occurring, we can see deep ocean trenches occurring. With convergent, where the plates move together, we again can see trenches being formed, we can see volcanoes forming, we can even see mountain ranges forming. We also can see, for the most part, with transform boundaries, we tend to see that be an area where we see a lot of earthquakes occur, because they keep the plates rub against each other and they get stuck, and then as they get stuck after a certain point, they push away from each other, and that's what causes an earthquake. So again, kind of just looking at to sum up, we're looking at three different types. Our next lecture, we'll look at kind of how plate tectonics occurs. What is the driving force for plate tectonics? To end this lesson, what I would like you to do is I'd like you to, in your notebook, draw each of the three types of boundaries and give an example of each. Thank you, and have a wonderful day.